everyone. In this video, we're going to look at example 2 in section 14.4 on gradients and directional derivatives in the plane. So in this example, we're going to have the opportunity to compute both a gradient and a directional derivative and to interpret them in the context. We've talked about the context and conceptual meaning of a gradient and directional derivative a little bit, but here we're going to start making it a little bit more concrete by looking at this example. All right, so in example 2, we are told that the fluid in atmospheres at the bottom of a body of water of varying depths, so the water changes in depth, is given by this function p of xy equals 1 plus x squared y over 100, where x and y are measured in meters. So we should think of this as, so we have a big body of water, maybe it's Puget Sound or a big lake, and we have some position xy in meters. And we want to know how much pressure we are at that position. So x and y might be somewhere located in the water, so we want to know how much pressure we have at that point. Okay, so we need to find the gradient of p at 1, 2, and the length of the gradient of p at 1, 2, and interpret them in the context of this problem. All right, so let's go ahead and get started. So first of all, the gradient of p of xy, recall, is just going to be the directional derivative with respect to x times I plus the partial derivative with respect to y times j. Okay, so we can go ahead and compute these. So here's our function p. So we can first compute the partial derivative with respect to x. So we're treating y just like a constant. So that would just give us 2xy over 100. And then we're going to include that I component. Plus now directional derivative with respect to y. So now x is just a constant. So that would just be x squared over 100 j. There we go. All right, so we can simplify this a little bit further, cancel the 5 and the 2 and the 100 to get 50. So this is just equal to xy over 50 I plus x squared over 100 j. Cool. So now we actually want to compute this gradient at the point 1, 2. We've already done all the hard work. We're just going to plug in 1 for x and 2 for y. So we get 1 times 2 over 50i plus 1 squared over 100 j. So that just becomes, simplifying some things, we get 1 over 25i plus 1 over 100 j. So here is that gradient vector. So what does the gradient tell us? Well, we haven't said this explicitly, but what we saw in our observation from the preliminary example is that the gradient of our function at a point tells us the direction of the maximum change of our function. So in our case with pressure, this vector tells us the direction of maximum pressure increase. So again, notice the gradient is a vector. And so it tells us the direction of the inputs that would lead to the largest possible change of output. Okay, so now let's consider the length of our gradient vector. So here we're just going to find the square root of the squares of both components. That's how we find the length or magnitude of a vector. So we have 1 over 25 squared plus 1 over 100 squared. And we take the square root. You can compute that in your calculator. You should be getting about 0.041. And while we're at it, we can think of the units of this gradient vector. So the gradient vector, again, it's telling us the direction of maximum pressure increase. So the units on it should actually be the output values with respect to the input values. So this would be measured in atmospheres per meter. And how do we interpret the length of the gradient? Well, the length of the gradient actually gives us the magnitude of maximum pressure increase. So meaning how much our temperature is increasing in the maximal direction. magnitude of max pressure increase. Okay, so nice work so far. So let's go ahead and we talked about interpretations of both of these values already, but let's go ahead and make it a little bit more concrete. So I'm going to write out the interpretation. Interpretation. So we're looking at the point 1, 2. And we're considering the fluid pressure, how the fluid pressure increases. And so in particular, the fluid pressure increases the fastest if we move in the direction of the gradient vector. So I'm not going to write out that vector. But that's the interpretation of that gradient vector. And if we move in that direction, I'm going to write down here to continue my work. If we move in that direction, the pressure will increase at 0.041 atmospheres per meter that we move. Okay, so I really encourage you to pause the video at this point and reflect on these two interpretations, or rather the interpretation of both that gradient as the direction of pressure increasing the fastest, and the length of the gradient as how much the pressure will increase if we move in that direction. All right, and when you're ready, we'll continue the video and look at part B. So for part B, we're asked to find the directional derivative at 1, 2 in the direction of u, where it says u is a vector, a unit vector in the direction of the vector 3i minus j. We also want to give an interpretation of our answer. So first we need to compute what u, the unit vector, will be. So to do that, we're going to start with our vector 3i minus j, divide by the length of our 3i minus j vector. So that would be the square root of 3 squared plus negative 1 squared. So that would look like 3i minus j over the square root of 10. So that would look like 3 over root 10i minus 1 over root 10j. Okay, so there's our u vector. So to compute the directional derivative in the direction of u at 1, 2, we're going to need to take the dot product of the gradient at 1, 2 with our unit vector. So looking at that gradient from part A, we see that we would get 1 over 25i plus 1 over 100j dotted with 3 over root 10i minus 1 over root 10j. Okay, not too bad. So now we just multiply components and add together. So when you do that, you should be getting something close to, I'm just going to speed ahead here, but please pause the video to actually compute this on your own, 0.0348. And as far as units, the units of our directional derivative would be those output units, so atmospheres per input unit meter. So what is this number telling us? Well, this is a rate of change, a directional derivative, and it's telling us how much the atmosphere of pressure changes per meter as we move in the direction of u, starting at the 0.12. Awesome. Well, great work, everyone, going through these calculations and this example. Please feel free to rewatch any parts of this video to help this material become more comfortable and so that you can do some problems on your own. Keep up the hard work.